Hello viewers, in today's session we are going to discuss another important and very conceptual problem from functional equations, right? So viewers, we have already discussed a lot of problems related to functional equations, and here in this class we are going to discuss this problem in which we are given a function f from R to R, where R is the set of real numbers, and this function f, it satisfies this functional equation, that is f of x plus y is equal to the product of f of x and f of y for all values of x and y belonging to the set of real numbers. And here an additional condition is also given, that is f of x is not equal to 0 for any x belonging to the set of real numbers. And here we are given that f of x is differentiable at x is equal to 0, and the derivative of f of x at this point is given as f prime of 0, that is equal to negative of pi, right? So using all these conditions, we have to find the function f of x, right? So let us start, and here we'll solve this problem with the help of the concept of partial differentiation. So here we are given the equation, that is f of x plus y is equal to f of x and the product of f of x and f of y for all x and y belonging to the set of real numbers. Now let us take x is equal to 0 and y is equal to 0 in this equation. So we have f of 0 plus 0, and here we have f of 0, and here we have f of 0. So this is f of 0, and here we have the square of f of 0. Now we can take the square of f of 0 to the left hand side. So we have f of 0 minus f of 0 square, and this is equal to 0. Now we have an equation here. So let us take f of 0 common. So we have 1 minus f of 0, right? And here we can see that we have two factors. The first one is f of 0 minus 0, because we can take f of 0 as f of 0 minus 0, and the second product is 1 minus the second factor is 1 minus f of 0. So here we can now write f of 0 is equal to 0, or we can have 1 minus f of 0 is equal to 0. So this is f of 0 is equal to 1. So from here we get two values of f of 0. The first one is 0 and the second one is 1. Now see here we are given this condition, that is f of x is not equal to 0 for any x belonging to the set of real numbers. So here f of 0 cannot be equal to 0. So we'll discard this value, that is f of 0 is equal to 0, and will accept this one, because here f of 0 is non-zero, right? So f of 0 is equal to 1, so we'll accept this value. Due to this condition, we'll discard f of 0 is equal to 0. So let us take f of 0 is equal to 1, right? So the purpose of taking x is equal to 0 and y is equal to 0 is to get the value of f of 0, right? Because in the later steps we are going to use this value. So now let us differentiate this functional equation both sides partially with respect to x, right? So in the first step, what we will do will differentiate both sides partially with respect to x. So we have here f prime of x plus y, and by chain rule, the derivative of x is 1 and the derivative of y is 0, because when we differentiate partially with respect to x, then y is treated as constant. And here we have f of y as constant, so we have simply the derivative of f of x. So we have f prime of x and f of y. So let us call this equation as equation number 1. Now in the second step, we'll differentiate both sides partially with respect to y, right? So in this case, we have f prime of x plus y here, and by chain rule the derivative of x is now 0, and the derivative of y with respect to y is 1. And here when we differentiate both sides partially with respect to y, now x is treated as constant. So here we have f of x, this is treated as constant, and here we have f prime of y. So let us call this equation as equation number 2. Now equation 1 can be simply written as f prime of x plus y, because here we have 1 plus 0, that is simply 1, and here we have f prime of x and f of y. And from the second equation, we can now write f prime of x plus y, and here we have 0 plus 1 equal to 1, and here we have f of x and f prime of y, right? Now look at these two equations. So here the left hand sides of both the equations are equal, that is f prime of x plus y. So we can equate the right hand side, right? So we can now have from these two equations, we can write f prime of x, f of y is equal to f of x and f prime of y, right? So now we have a very important step over here, and here what we will do, we'll replace y by 0, right? We'll keep x as such and we'll replace y by 0. So we have now f prime of x, here we have f of 0, and here we have f of x, and here we have f prime of 0, right? Now see, f of 0 is we have already calculated, f of 0 is equal to 1, and we are given that f prime of 0 is equal to minus pi. So these are the two conditions which can be utilized over here. So we have f prime of x, here we have simply 1, and here we have f of x, and f prime of 0 is minus pi, right? So now let us rearrange this equation. So we can now write f prime of x divided by f of x, and here we have simply minus pi, because this equation can be written as f prime of x, and here we have minus pi f of x. So now from here we have this equation. Now this is our differential equation, and we can easily get the value of the function f of x if we integrate both sides. So now integrating both sides with respect to x, we have f prime of x over f of x. Here we have dx, and here we have minus pi dx, and c is the constant of integration, right? Now see, this is a well-known form in indefinite integral, because if we have an integrand in which the numerator is the derivative of denominator, then the integral of f prime of x over f of x is simply a log of f of x, right? So the indefinite integral of f prime of x divided by f of x dx is the natural log of f of x, and here we have minus pi, and this is dx plus c, so we have minus pi x plus c. So now we have this equation, log of f of x is equal to minus pi x plus c. Now this constant of integration c, it can be easily determined by using this condition, that is when x is 0, then f of 0 is equal to 1. So let us take x is equal to 0 in this equation. So we have log of f of 0. Here we have minus pi times 0 plus c, and f of 0 is 1. So we have log of 1 is equal to 0 plus c, and that is c is equal to a natural log of 1, that is equal to 0, because log of 1 is 0. So the constant of integration c is now equal to 0. So let us substitute this value of c in this equation. So we have log of f of x is simply equal to minus pi x plus 0, that is minus pi x. So now from here we have a natural log of f of x is equal to minus pi x, right? So in order to get rid of this natural log, what we will do, will take the powers of these two numbers, or will place these two numbers in the power of the exponential e. So we can now write e raised to log of f of x, and here we have e raised to minus pi x. So raising these two terms to the power of e, we have now this equation. Now e raised to natural log of f of x is simply f of x, because we know that e raised to natural log of a is equal to a, right? So here we have f of x, and here we have simply e raised to minus pi x, right? So this is the required form of the function f of x, where we have these conditions, right? And this function f of x, it satisfies this functional equation. So now this is our required function f of x, right? Now let us see how this function f of x, it satisfies this functional equation, right? So let us find out f of x plus y. So f of x plus y can be obtained by replacing this x by x plus y. So we have e raised to minus pi, and here we have x plus y. So this is e raised to minus pi x minus pi y. Now see, the exponential function, it obeys the laws of exponents. So we can now write e raised to minus pi x multiplied e raised to minus pi y. Now e raised to minus pi x is f of x, and here e raised to minus pi y is simply f of y, because in that case we'll replace x by y. So we have f of x plus y is equal to the product of f of x and f of y. Now we can write this function f of x as 1 over e raised to pi x, right? Now for all values of x belonging to the set of real numbers, we see that e raised to pi x is never equal to 0 by the property of the exponential function, right? So e raised to pi x is never equal to 0 for all x belonging to the set of real numbers. Hence f of x is not equal to 0 for all x belonging to the set of real numbers, and this is our given condition, that is f of x is not equal to 0 for any x belonging to R. And here we can also verify that f prime of 0 is equal to minus pi, because here the function f of x is an exponential function, right? And the exponential function is differentiable at x is equal to 0. So if we find out the derivative from this function, then the derivative of e raised to minus pi x is e raised to minus pi x, and here we have minus pi. Now if we replace x by 0, then we have f prime of 0 is equal to e raised to minus pi times 0, and here we have minus pi, and e raised to 0 is 1, so here we have 1, and here we have minus pi, that is 1 times minus pi, that is equal to minus pi, which is our required condition. So viewers, this is how by using the simple concepts we can solve these type of functional equations very easily.